Hello everyone, and thank you for joining us today. Welcome to AVO's webinar series. Today's topic is Basic Substation Configuration and the Components. My name is Ron Spatero, and I'm the Marketing Manager for AVO Training Institute. And I'll be your moderator for today's presentation and supporting you on technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. All attendees are eligible to receive one NETA CTD and one professional development hour. You will receive your attendance confirmation in an email within 2 business days after the webinar. That email will also include a copy of the PowerPoint presentation you're going to watch today, and a link to the recorded video of the webinar if you'd like to watch it again or share it with colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered after the webinar ends. Our presenter today is Greg Richmond, AVO Training Instructor and Training Specialist. Okay, Greg, let's get started. Thank you for joining us.
Thanks, Ron, and thanks, Mike, for allowing me to have this opportunity to conduct this webinar. I would also like to thank everyone out there in attendance as well. This is a good opportunity to spread good, powerful information on a basic subject for individuals who are been in this career field for quite a while. Today we'll be discussing just a few of the different types of power generating station systems, how they operate, along with the sub-grounding, and just a few of those components as well. We'll also be discussing the different types of substations and what they do within the power grid. We'll also be talking about some of the components within a substation, such as breakers, transformers, instrument transformers, and of course, safety. We can't forget safety. Let's go ahead and start out with our power generating system. So we've got 5 different types of power generating systems up there. We've got nuclear, fossil fuel, hydro, and wind and solar as well. Let's start out with nuclear power generation. So nuclear power generation reaction turns water into steam. Steam turns the turbines, and the turbines turn the generator, producing electricity. See, this slide really does a good job of showing exactly what happens with uranium fuel down here on the bottom, and how that heats up the water and turns the turbine, sends power through the generation and through the generator and on out to the customer as well. With our nuclear power plants, America's 99 nuclear power plants generate almost 20% of the nation's electricity. That's a large amount. Nuclear power plants boil that water, just like I said, with the reactor using their uranium fuel. Okay. Fossil fuel power is the next one online here. With a fossil fuel plant, much like a nuclear type station, water is turned into steam that is heated from the pulverization and burning of coal, which in turn drives turbine generators to produce electricity. Steam typically reaches temperatures of up to 1,000 degrees with pressures up to 3,500 psi being piped into that big turbine, spinning them giant blades of the shaft. You can take a look at this pic as well and see how that process works as far as that coal being burnt, heating up that water, spinning that turbine, and sending that power straight on down through the transmission lines. A little bit of information about fossil fuel energy. It's one of the most affordable, largest produced energy within the United States. Used to generate a substantial amount of electricity, about 37% of our nation's power is through fossil fuel power. The problem here, the real challenge is making sure that we find ways to burn it more clear as far as the environment is concerned. All right, let's get into a little bit of information about hydroelectric power. Inside the United States, there's about 80,000 dams all over the nation, but really only about 2,400 of them produce power. Other dams are usually used for recreation, stock farm ponds, flood control, water supply, and typical irrigation throughout whatever type of cities could be inside there. This particular type here is the most common type of hydroelectric power plant, called the impound facility. An impound facility is a large hydropower plant system. It uses a dam. To store the water in a reservoir. Water is released from the reservoir, flows through the turbine, spinning the turbine, activating a generator to produce electricity. You can see how this water is stored up on the other side of this dam, flows through this pipe, spins the turbine, producing a power through the generator and on down the line through the transmission lines. A disadvantage, of course, with the hydroelectric power compared to nuclear power is the hydroelectricity construction requires large spaces, and unfortunately it alters the environment and has a small footprint. Okay, next up on the box is wind power. Okay, this is a fairly up-and-coming power production system. It converts kinetic energy into electrical energy. It's done by using a wind turbine with propellers. The turbine is connected to a generator to generate electricity, and as the wind passes through the turbine, it moves the blades, which spins the shaft. Some of the advantages of the wind power is going to be obviously that it's a free fuel source because it comes from the sun, comes from the earth. It's environmentally clean. Another good thing about wind power is that it can mass produce wind machines in a factory, and it's also a renewable energy source as well. Some of the disadvantages as far as wind farms are concerned is that it's land sensitive, and unfortunately the wind doesn't always blow. Sometimes wind towers are normally noisy and unsightly. Aesthetically appealing is generally not an issue when it comes to, or generally an issue when it comes to wind power. A little bit of information as far as wind energy is concerned in the great state of Texas. As of 2010, the largest wind farm in the world was in Roscoe Wind Farms in Texas. It produces 781.5 megawatts of power. Wow. Just to compare that to the coal-fired generating plants, they average about 550 megawatts compared to this guy here that produces 781 megawatts of power. Last up on the bat is going to be our solar power system. Solar by far is going to be one of the cleanest type of power system and the most reliable, renewable type of energy system as well. What happens here with solar? What happens here with solar-powered photovoltaic panels convert the sun's rays into electricity by exciting electrons in silicon cells using the photons of light from the sun. Take a look at this example here on this slide. You can clearly see a simple diagram demonstration of how this works. Sun comes into solar panels through a charge controller. Battery system then gets the power, converted to either a DC type system or an AC type system, whatever is needed for the customer out there in the field. Okay, so this next one here is a good demonstration of the three major bulk power grids within the U.S. Most of the power delivery systems are all tied together. Okay, the United States has one of the world's most reliable and affordable and clean electric systems. But unfortunately, it faces a lot of major weaknesses out there with respect to physical threats from severe weather, terroristic attacks, and of course, the most newest common one is going to be our cyber threats. So they are all tied together to provide a reliable source of energy for the end customer. So this, once again, like I said, this slide kind of gives a demonstration of the western grid, the eastern grid, and then on the bottom down here we've got what's called ERCOT. So ERCOT stands for the Electrical Reliability Council of Texas, and it operates the electric grid and manages the market for 75% of Texas. Okay, so let's go ahead and move right into what's the real purpose of a substation. So just a couple of bullets here that I wanted to talk about with the substation and its definition. So it's critical for generation, transmission, and distribution systems. So we'll get into, within this webinar, the differences between generation. We've already talked about generation, but we'll get into the difference between transmission and distribution and how those different factors play into providing power directly to the customer, of course. Next one we'll talk about is it performs several important switching functions. So these switching functions could be used for different reasons out there, such as performing maintenance, could be used such as for emergency purposes and so forth. May have various voltage levels before it actually reaches the customer. And that makes a lot of sense because we may need to send that voltage out at a higher level or at a lower level, step it up or step it down, depending on what that customer may need or what that industry may need out there. And the most important is that it's going to be owned and operated by an electrical utility or a large industrial commercial customer. Someone has to claim ownership on this system, and they also have to perform maintenance on the system as well. Using a SCADA system for a remote supervision and control, of course, in order to locate those faults, in order to open and close those circuits, in order to monitor that system in the event that something truly does go wrong, which ultimately is what we're all trying to avoid. So I wanted to bring up the three different types of potentials that you could find inside of a substation. These are the main three that we're going to kind of focus on. So IEEE standard 80-2000 talks about these, and these types of potentials are step, touch, and mesh potential. So step potential or touch potential is the voltage between the energized object and the feet of a person in contact with the object. Touch potential could be nearly the full voltage across the grounded object if that object is grounded at a point remote from the place where the person is in contact with. So the key here with touch potential, of course, is going to be that difference between what that person is touching and the grounded object. The next one's going to be our step potential. Step potential is the voltage between the feet of a person standing near an energized grounded object. A person could be at risk of injury during a fault simply just by standing near that grounding point. And then, of course, mesh potential is a factor calculated when a grid of grounding conductors is installed. Mesh potential is the difference between a metallic object connected to the grid and the potential of the soil within the grid itself. Just a little bit of an idea of the different types of potentials that you could see within your substations according to IEEE standard. I like this slide because it kind of breaks down and gives you an idea about touch and step potential. So we've got an induced fault current coming in on the top of this big H frame transmission line going down, and it represents the step potential with this individual on the left and how current can flow through a person's body between 2 points. And then, of course, on the right-hand side, we've got touch potential and how that individual is touching the main frame of that line and current's flowing through his arm, down his foot, into the earth. Soil resistivity, of course, plays a large factor with these two different types of potential as well. All right, let's move on to our earthing materials when it comes to the interior portion of a substation and grounding. So we're going to be discussing conductors, connections, rods, and fencing. So I like this shot here. I like this picture because it kind of breaks down the internal portion of a substation on a basic level, even when it comes to grounding. So we can see our copper internal grounding grid underneath the crushed rock, and we've also got a transformer. You can see how each component of this internals of this substation are all grounding to include each part of the fence as well. So we've also can include the fact that every component inside of this substation is all going to be grounded, to include gates, to include any light poles, along with lightning protection as well. Okay, so let's talk about our conductors and rods real quick and see what IEEE standard says about that. IEEE standard 80-2000 discusses thoroughly our conductor sizes, our K-factor in relation to fault. We'll talk a little bit about K-factor and its relationship to the connections, current capabilities in cycles and clamps, and of course, conductor sizing is important as well. We want to make sure that everything matches and in relation to the fault current. Choosing a conductor with relations to corrosion problems. Typically, what we're going to see out there from IEEE is going to be three types of conductors out there as far as a copper conductor, a copper-clad steel conductor, and aluminum and steel type rods out there. So what IEEE says in IEEE Standard 80 TAC 2000, just to give you a little bit of information about that, it says directly that each part of the grounding system, including the ground conductors, all connections, connecting leads, and all electrodes should be so designed that for the expected design life of the installation, the elements will have sufficient conductivity so that it will not contribute substantially to local voltage differences, resist fusing and mechanical deterioration under the most adverse combination of fault and magnitude and duration. And for me personally, I think that this is one of the most important, that it has to be mechanically reliable and rugged to a high degree. Be able to maintain its function even when exposed to corrosion or physical abuse. So I got an example of some different types of connections that you could see inside of a substation. So we've got exothermic type welding. We've got a mechanical down there on the far right, and we've got a crimped demonstration in the middle down there below that mold, that exothermic mold. So exothermic welding, of course, is going to be the most reliable portion. And the way that this process works, that it employs molten metal to join those conductors, because that's ultimately what we want to try to achieve, is the exact same replication of that conductor that's inside that system. With exothermic, it allows that with the best capacity. The process with this exothermic reaction is a thermite composition to heat the metal using an aluminum powder and a metal oxide. It requires no type of external source or heat unit. What this is trying to tell us to do is that we'll take this molten metal and aluminum, metal oxide and aluminum, heat this metal oxide and aluminum inside, and it causes an exothermic process, a welding process that sends that molten metal down to these three different, this is a T type of exothermic connection, down to this through the mold to the bottom part of this to connect these three types of conductors in a welding process. Of course, with this welding process, you want to make sure that once it's done, let it dry, let it cool, and then when it's done cooling, clean it off. There will be some slag that will be on top of this exothermic weld. Just hit it with a metal hammer, kind of break that slag off a little bit, and then hit it with a wire brush and coat it with a grease. With the mechanical type connector down here, this is a fairly simple one. This one may be subjected to a little more corrosion because it could come loose because it is a mechanical connection. Iron oxide is a key here with the problem situation, and then we've got crimps, solid crimp in the middle down there that is a little bit more reliable than a mechanical type of connection as well. But all of them are going to play their own key roles within the grounding system. I wanted to touch on a little bit more with IEEE Standard 80 TAC 2000 and let you know what IEEE says about the connections within substation grounding. So it says that all connections in a grounding network above and below ground should be evaluated to meet the same general requirements of the conductor used, which is exactly what we were talking about with the exothermic type welding. We want to make sure that we meet that same requirement of the conductor as far as electrical conductivity, corrosive resistance, current carrying capability, and mechanical strength. It says a little more about how the connections should also be strong enough to withstand maximum expected fault currents and be able to resist corrosion for the intended life of the installation. If you're interested, IEEE Standard 837 TAC 1989 gives a little bit of detailed information on application and testing of these type of connections inside of a substation grounding system. Now, unfortunately, with time constraints, we could talk all day about grounding and substations and so forth, but we've got to keep moving on. We'll get into fences now a little bit. All right, so the National Electric Safety Code is our go-to when it comes to grounding fences as well. And it's used, and it's going to give us, it requires that grounding metal fence is used to enclose substations with energized electrical conductors or equipment. It says that we need to bond the fence to the grid or to a separate underground conductor directly. It's important because the fence is going to be available to the public. And we want to make sure that that our public is taken care of as well, because they don't know what's going on inside there. We want to make sure that they're safe. The NESC, National Electric Safety Code, does talk a little bit directly about how that the substation grounding system should be such that touch potential on the fence is within calculated tolerable limit of its potential. Step potential is usually not too much of a concern with the fence perimeters, but it should be checked to make sure that the problem does not exist. Also, a little bit more on the NESC. The NESC does break down all the grounding methods for bonding for fences. Okay. A little bit more information on fences as far as the National Electric Safety Code is concerned. All right, so we're going to start dipping into a basic substation layout here. So this gives you a breakdown of how the system is being fed. We've got a 34K line coming in through the transmission lines, sub-transmission lines, goes down through the lighting arresters, through the air brake switches, down through the oil circuit breakers for protection, and it goes through these. It goes back into the step-down transformer, through the voltage regulators, hits our metal clad switchgear distribution bus, cutout switches, all controlled through the control house inside there, and it goes on out to distribution lines. So we are going to be talking about the different types of transmission types out there, substation types. So we'll be getting into a step-up type transmission substation. We'll be talking about our step-down type transmission substation, distribution substation as well. Unfortunately, with time, I can't dip too much into your bulk transmission substations or your collector substations, which have to do with your wind type energy production devices. But these are going to kind of break down your basic substation types and what you may find inside. Okay, so step-up transmission substations. Let's start out with that. So a step-up transmission substation is generally going to receive power from a power generating facility and uses large power transformers to increase that voltage for transmission to way far off locations. All right, there can also be a tap on the incoming power feed from the generation plant to provide electric power to operate equipment inside of that generator, inside of that generation plant. Substation can have circuit breakers that are used to switch generation and transmission circuits in and out for emergency or as needed operations. Our step-up transmission system is generally going to range anywhere from 155 kV to 765 kV. Okay. Next up is our step-down substations. Our step-down transmission substations are usually located at switching points in the grid, and they connect these substations along the grid as well. These step-down substations can change the transmission voltages to a sub-transmission voltage, usually around 69 k. The sub-transmission lines are connected to the distribution type lines. And we'll get into distribution substations here in just a second. Sometimes you may see out there in the field that a sub-transmission line can be used, tapped off into an industrial facility to provide power to that industrial facility. Otherwise, the power goes straight to a distribution type substation. Okay, next up on the bat is our distribution substations. So these are typically gonna operate around 2.4 to 3.5 34.5 kV. Deliver power directly to anything from industrial or residential customers. These distribution feeders transport power from the distribution substations to the end customer. These distribution transformers transform the distribution voltage to the service level voltage directly to the houses or any type of industrial plants from 110 volts up to 600 volts. All right, so we talked a little bit about substations, just barely touched on substations and what they do out there in the field as far as stepping up or stepping down, a little bit about power generating systems. So let's get into the different types of substation equipment that you can see out there. Just a basic, and like I said before, we're unfortunately, due to time, we're not always going to be able to get into all the other different types of equipment out there, and I get it, but we'll at least kind of touch on a few of the most important pieces out there. So first up, we're going to talk about transformers. We'll talk about switchgear, a little bit about circuit breakers, overcurrent protected devices, relaying and metering devices as well. So the most important one out here that we could see is going to be our transformers. And our transformers' sole purpose in life is to raise and lower the voltage to serve transmission or distribution circuits. This is its sole purpose. This is what its job is to raise or lower the voltage, depending on what that customer needs or how far along that power may go. Our transformers typically are going to be rated in power, whether it be MVA or KVA, insulation type, as far as the cooling insulation, voltage rating, winding connections, whether it be a delta, Y, delta, delta, Y. Voltage regulation as far as the tap changes is concerned on the high side or on the low side. Class is another way that a transformer could be rated in as far as cooling design is concerned. It has fans or anything attached to it. BIL, basic impulse level. All right. Impedance is another one. But what it really comes down to is what the customer really needs and what that transformer is going to be based off of as far as its design is concerned. This is an important subject here that I feel is sometimes overlooked, and it's the nameplate data of a transformer itself. So this nameplate data is going to be something that is important because it's going to tell you what the personality of that transformer is, in my mind. It's going to tell you what that transformer is all about. It's going to tell you what that KVA is. It's going to tell you what the rise in temperature is going to be for that transformer. Its serial number, any manufacturer's information, wiring, internal wiring. Important to know, though, of course, is that nameplate data aren't always accurate. We are human. Humans do make mistakes. So we want to make sure that we verify that this nameplate data does match the transformer, and we can do that through testing processes. Okay, so let's go ahead and get into a little bit about switchgear. All right, switchgear can be either indoor or outdoor, or a combination of both. Most outdoor switchgear is going to be rated around 26 kV. Indoor is going to be above, and most indoor switchgear is going to be below 26 kV. Different types of switchgear you could see out there is going to be our load interrupting type switchgear, load break switches, disconnect switches, main bus connectors, and of course that switchgear is also going to include insulators and secondary devices for monitoring and control. Switches that are used for oscillation, load interruption, and transferring service between different supplies. Okay, let's see, what else can we talk about? Load interrupting or load break switches combines a function of disconnecting switches and a load interrupter for interrupting at rated voltage and currents not exceeding the continuous current rating of the switch itself. Okay, most of the time you may see an automatic transfer switches out there. They're double throw construction. They're usually used for emergency and standby power generation systems rated at 600 volts or lower. A little bit about circuit breakers. Let's get into some circuit breakers for a little bit. Their sole purpose is to open and close a circuit either automatically or manually. So that's their sole job. That's their purpose. They're basically just a big, dumb operational piece of equipment that does exactly what it's told, whether it be to open or close automatically or manually. Of course, these automatic controls are going to come from different types of devices out there that could be used to control these circuit breakers. All right, so these automatic circuit breakers operate on a predetermined overload without damage, meaning that we want to operate this circuit breaker without damaging it. They're designed to operate and terminate the current very quickly, and this is done, and their arc is extinguished between 30 and 150 milliseconds after being tripped. So some of the circuit breakers that we could see out there are going to be our air, vacuum, SF6, and oil. The most common is going to be SF6 and vacuum. All right. Both connections to a bus bar or wires, especially in outdoor switch yards. Often going to be draw-out type construction. Allows a breaker to be removed using a motor-operated hand crank mechanism. So this is telling us that we can either remove that circuit breaker via a motor type or a hand crank type, depending on that type of bus bar that it's attached to. So a little bit about air circuit breakers. Okay, air circuit breaker is a simple construction. There is going to be a main set of contacts, an intermediate set of contacts, and then of course an arcing set of contacts. So within your arcing contacts, of course, those are going to be our contacts that are going to make first and break last. Those contacts are designed to prolong the life of the main contacts. So with this air type of breaker, we've got a real good demonstration, a good cutout of an arc chute, all right, and how the arc chute works. So the arc chute is designed to accept that arc when the breaker opens up, and there's going to be a small puff of air. There's going to be a small puff of air that's going to shoot that arc up into the arc chute, and the objective behind this arc chute is to achieve what's called current zero through our blowout coils internally of this arc chute here. It's going to help extinguish that arc. So you can see down here on the bottom, we've got a set of main contacts down here in our arcing contacts and intermediate contacts as well. This is a simple type of a breaker setup. Okay, we talked a little bit about stabs in the back. These are our stabs that are going to go directly into the bus bar, and they're only going to go in whenever those shutters in the back of that bus bar open and close. Okay, and another one that I feel is of a simple operation is a vacuum type of a circuit breaker. So with this vacuum type of circuit breaker, we've got a set of butt contacts internally, and these butt contacts are obviously going to open and close via this movable shaft. Okay, we've got a metal vapor condensing shield that surrounds the electrical contacts on the inside, and then we've got this insulating envelope on the outside that's usually made out of glass and porcelain. Okay, now the sole purpose behind the metal vapor condensing shield is to prolong the life of this insulating envelope, because this insulating envelope is going to be damaged in the event that these electrical contacts open and close. The flexible metallic bellows allow those contacts to open and close and still be able to maintain that internal vacuum of this bottle. Okay, this vacuum type circuit breaker utilizes a vacuum internally to extinguish arcing when the circuit breaker is opened up, and it's used to act as a dielectric to insulate the contacts after the arc has been interrupted. Unfortunately, though, with this type of a circuit breaker, with this type of an arc interrupter, when these bottles go bad, it's normally the operation is just to replace the bottle and with a new bottle. But of course, anytime that you replace the bottle, with one bottle, you want to make sure that you replace all 3 bottles. So the flexible metallic bellows, of course, like I said, are going to allow that movable shaft to move back and forth and still allow those contacts to open and close under a vacuum. Once we lose that vacuum, of course, then that guy's no good. As far as testing is concerned with this vacuum type of bottle interrupter, really the only test we can perform on this in order to check this vacuum bottle is going to be our vacuum bottle integrity test used with an overvoltage withstand tester, applying a DC voltage and testing this. And of course, it is a go or no go type test. All right, it's either a pass or fail test. That's all it is. All right, so our SF6 type breaker, sulfur hexafluoride type breakers, uses gas to extinguish the arc internally. This type of breaker it has excellent dielectric and arc quenching capabilities. All right, it's easy to maintain. All right, as far as it being compared to the oil or air, it is superior because of its long life. It's a simple construction, easy to maintain. Contacts open and close internally, and SF6 helps to extinguish that arc, helps to minimize that arc internally. So our last one here that we're going to talk about is our oil circuit breaker. And of course, this oil circuit breaker it's a little kind of an older type of a breaker. Most of these breakers are getting replaced, okay? But ultimately what it comes down to is we've got a movable contact down on the bottom, and those contacts are obviously going to be moving up and down in the event that we need to open or close the circuit breaker. And so the oil itself is what's going to provide that cooling and help to extinguish that arc as well. There is a little bit more maintenance involved with an oil circuit breaker. We have to test the oil, we have to test the contacts, we have to do a tank loss index test on this particular type of circuit breaker. But these are generally going to be moving out of the industry a little bit more and being replaced with something a little more reliable like SF6 or a vacuum type breaker. The thing about an oil circuit breaker is that all three phases of normally with smaller oil circuit breakers, you can put all three phases into one tank. Whereas with the larger oil circuit breakers, you may need to put each phase into its own separate type of tank. So on the outside of this here circuit breaker, we've got a control box that's mounted to control the operation of the contacts and the moving contacts internally. And lastly, we'll talk a little bit about instrument transformers and give you a little bit of a rundown on CTs and PTs. I'd love to sit here and talk about CTs and PTs and make a 30-minute discussion about CTs and PTs, but unfortunately we don't have all that time. So our instrument transformers are going to help us accurate devices to help us isolate these type of circuits. They're going to help us operate instruments or metering from high voltage or high current circuits. Are used to relay critical information in phase relationship for communicating and metering purposes. So the two types of CTs or the two types of instrument transformers we could see out there is going to be our current and potential types. So let's get into a little bit about CTs and PTs. Current transformer is a type of transformer that is used to measure AC current. Okay, it produces an alternating current which is proportional. Okay, proportional meaning that there's a ratio. Usually that ratio is going to be a 5-to-1 ratio. All right, it's going to be proportional to that current on its primary. Current transformers are the current sensing units of the power system, meaning that in my mind, that these current transformers are going to be our eyes of our substation, and they're going to see any type of problematic situations, and they're going to be able to recognize it, and they're going to be able to control that breaker to open that circuit under a fault condition. With our potential transformers, okay, in theory, really all a potential transformer is just a step-down transformer. Okay, it has a lower turns winding than its secondary, of course, and they're designed to present load to the supply being measured with an accurate voltage ratio and phase relationship to allow secondary metering. So they're going to give us that opportunity. They're going to give us that opportunity to see what that voltage is on the secondary side, and find out where our substation is really at within the grid. All right, so let's talk about safety. Just a little bit of safety here within substations. So you can't have a discussion about anything with electrical and not talk about safety. All right. And the first bullet up there, one of the most important bullets, I think, is ensuring that qualified personnel enter into the substation. This is important because we definitely don't want to put people in harm's way. We want to make sure that the people are in the substation need to be in the substation. So qualified person, 70E talks about a qualified person, and it's a full-fledged paragraph, and it talks about what the qualifications are and what makes a qualified person a qualified person. So let's make sure that we put the right people inside of that substation. The next one is going to be exercising caution near overhead conductors. So that's important. We've got a lot of overhead solid bus bars within a substation. Sometimes those solid bus bars could have a protective cover over them because of birds and whatnot with their wingspan and so forth. You may see that sometimes, but we want to make sure we keep a good use of situational awareness within inside of the substation. Make sure we don't come in contact with any of those conductors. Operating any type of machinery is important. Whenever we're doing testing inside a substation, we could be using ladders inside the substation. So make sure that we don't come in contact with them. Don't get in line or maintain our boundaries within those substations as well. Be aware of step and touch potential. That's an important one. We want to make sure that we test our connections inside of that substation and make sure that all of our connections are good, solid connections. Make sure none of them are broken. That's going to mitigate any type of touch potential that we could incur inside of our substation. As far as step and touch potential is concerned, I want to talk about making sure that we keep our vegetation inside of the substation out. Okay, we don't want to need any vegetation. We want to make sure that we keep any type of rodents out of there. We want to make sure that that crushed rock that's inside of that substation is kept at a nice thick amount according to the IEEE standard, and so that we have no potential for flooding as well. Utilizing proper PPE is important. All these different substations are all going to have different types of voltages in them, different types of incident energy levels, so we want to make sure that when we're doing work inside of these substations that we maintain the correct PPE, because it's for arc flash and arc blast. Close all gates before you leave and any time that you enter into a substation. Close all your gates behind you. We want to keep people out, like I said, that don't need to be inside of that substation. Just keep them out and make sure that we don't let anything else inside, any wandering people or anything like that. Observe all warning signs. This is important. This picture here on this slide is an approved danger high voltage keep out sign. So make sure that all of these warning signs and these barricades and we exhaust all of our resources to make sure that the right information is on these substations so that we let people know that, hey, there's a hazard inside here. Stay out. I want to make sure you're safe. And of course, the most important is we want to make sure that we leave it clean and neat. Anytime we come into a substation, and there's trash, or if there's weeds, or maybe a bird may have come in contact with our line, or unfortunately a squirrel or something like that, that we we leave it better than we had it before. We leave it better than we had it before, and that so that way the next person can come in and they know exactly what to look forward to, and they know that that this substation was kept up like it was supposed to, and that the person who came in there before did a good job and made sure that that it was correct like it was supposed to. All right, so let's go ahead and finish up. So we talked a little bit about types of power generating system. We briefly discussed our different types of plants out there as far as nuclear power plants. We talked about the fossil fuel power plant, hydroelectric type power plant. Briefly talked about our wind power plant and its advantages and disadvantages. Solar power plant is another one we talked about. Kind of discussed about the different types of ways that they produce power and send that power to our substations downrange to provide power to the customers themselves. I gave you guys a little bit of information about a power grid and how the United States is divided up into 3 different sections. And we talked about how they're all integrated and tied together. I talked about step potential and touch potential and how important those 2 different types of potentials were with substation grounding. So I know I spent a little bit of time on grounding, but I feel that it's one of the most important pieces about the substation is making sure that that grounding grid that's usually designed by engineers is done correctly in order to mitigate any type of a catastrophic life failure or whatnot. Step potential and touch potential we talked about and the differences between the 2. Talked about grounding and the different types of standards that you could see out there in the field to help you maintain and help you install your substation grounding systems. IEEE standard 80 TAC 2000 was one that I used. I used that for conductors and connections. I also talked briefly about IEEE standard 837 1989, and then of course we dipped into the National Electric Safety Code as well. Okay, then we talked a little bit about substation transformers as far as step-up transmission substations. We talked about our step-down transmission substations, and we also briefly talked about our distribution substations and the key roles that each of these different substations play within this grid. Distribution substations is where our lines are going to be distributed out to the customer. And we briefly got into transformers, talked about a basic rundown about transformers, and we talked about the nameplate data, and then of course we talked about switchgear, broke down switchgear, the different types of circuit breakers, finished it up with PTs, CTs, and then lastly safety. All right, well I'm going to go ahead and pass this on to Mr. Ron.
Thank you, Greg, for that presentation. We're excited here at AVO Training Institute to have a special offer for all our attendees today. We've got 2 substation courses, Substation Maintenance 1 and Substation Maintenance 2. And we're offering those 2 courses at a special discounted rate if you register and attend before November 30th, 2017. You can go online to avotraining.com to register for these courses, and be sure to enter the promo code November to get this discount. Again, we're excited to offer this to you attendees today in our way of saying thanks for listening. We also would like for you to save the date for our next webinar. It's going to be Tuesday, November the 14th, same time, same place, 1 p.m. to 2 p.m. Central Time, and we're going to cover the NFPA 70E 2018, What's Changed? Our presenter for this webinar is going to be Dennis Neitzel. He's our Director Emeritus and actually is a principal member of the NFPA 70E Technical Committee that's comprised of about 35 different individuals from around the world, around the country. So we're really excited to have Dennis on board to be able to explain these changes because he's taken part in helping make the changes. So please save that date for us. Again, November 14th. Of this year. The webinar has concluded, and we'll take the time to answer some questions in the remaining time that we have. Remember, you can submit your questions in the Q&A box that's on your screen there. A copy of the presentation will be emailed to you in the next few days. Also, a recording of this session will be available on our website under the Resources tab at avotraining.com/webinars. All our webinar series are recorded there in case you've missed the past webinars that we've done here over the last few months. Okay, let's get to some of these questions, Greg, in this time that we have left. Elizabeth wants to know, what is a SCADA system?
That's a good question. So the SCADA system is going to be a monitoring system within your electrical utilities. It's going to be able to monitor any type of problem situations. It's going to monitor the power, load balancing, and so forth, and allow that that system is going to allow you to locate any type of faults down range and be able to localize problem situations so that when the technician goes out there, he's able to spend more time fixing the issue than he is trying to find the issue.
Okay, thank you, Greg. We've got a question here from Richard. Wants to know a little bit more of a clarification on what makes for the minimum required qualifications to enter a substation.
That's a good question. I'm going to go ahead and we're going to send that one to an email to you because I really want to focus on what the standard has to say on the entrances, the qualified people who are allowed to enter into a substation.
Okay. The other question here is, for vacuum bottle integrity testing, if you fail the DC withstand test, does that mean the bottle has failed, or do you have to confirm its failure by performing an AC hypothesis?
That's a good question. There's always that big argument between DC and AC testing. Okay, your manufacturer's specifications are going to promote more AC testing than DC testing. So in reference to failure, yes, when that vacuum bottle does fail, that overvoltage withstand test, it does need to get replaced because that vacuum internally has been lost with that interrupter.
Okay, this may be a related question. DC testing a vac bottle has dangers such as X-rays. Some manufacturers state maximum linkage current when doing a withstand test and state if bad, values should be found during the DC test.
Okay, let me talk a little bit about X-rays. Let me talk a little bit about X-rays until Ron gets a question. But here we go. Go ahead, boss.
The end of that question is, during a DC test, you have to perform an AC test prior to condemning the bottle.
Okay. DC testing a vacuum bottle, dangers such as X-rays. Okay, you're right. There are dangerous X-rays that can occur during DC testing, but those X-rays are really only going to occur when the bottle fails. Okay, just keep that in mind. We want to make sure we keep that minimum. The standard distance is going to be about 3 feet.
Does wet weather increase the touch potential?
Oh, absolutely. The body's resistance plays a huge factor when it comes to resistance and any type of potential when it comes to contact with an electrical conductor. So lots of factors are going to play with that one. A person's weight is going to play a factor. The internal resistance between hand to hand, hand to foot, foot to foot. Each body is going to produce its own different amount of internal resistance. So humidity plays a factor, whether or not what you've eaten, all these different things play a factor, of course, with resistance.
Tim wants to know, does the SF6 gas become compromised after so many operations?
Well, in my past, the only real problem that we've had with SF6 is that it leaks. Okay, so just keep that in mind with SF6.
Tim also asked the question. They say they have two 115 kV SF6 breakers, and about 102 operations on them. Does that play a part in the compromise?
All right, I'll tell you what, Tim. I like your questions about your 110 operations, but my real question is maybe are those operations due to maintenance or are they operations because of faults? So what I want to do with that one in particular is I want to send that one to an email, and I want to kind of clarify a little bit later on that one.
Okay. What method is used to measure the crushed rock layers to ground grid?
Okay, measuring crushed rock layer to ground grid. Well, your initial layout from your engineer is going to tell you exactly how much crushed rock is going to be internally on that substation. That crushed rock is going to settle, so you'll have to get out there and measure it.
Question has come in, will we be having an arc flash training scheduled in the coming months? You can be sure we will. Check abotraining.com where you can download one of our catalogs, and you'll see that we have a full list of courses scheduled throughout this year and into the next year. Question from Dave, how does the variable frequency transformer work?
Yeah, let's get into that one a little bit later, Dave. We'll get you on that one. William,
is a CAD weld UL approved?
That's a real good question. I've done probably 1,000 different CAD welds. Now, let's not confuse. CAD weld is a specific name of a company. We want to call it exothermic welding, but it is approved. It is an approved method of marrying two different pieces of material. I find that exothermic welding is the most effective way of meeting the same properties as a conductor, whether it be lightning protection systems, grounding grids, facility grounds. It doesn't matter.
Greg, we only have a couple more minutes left for our Q&A. If we don't get to your questions during this session, we will be sure to email you the answers to your questions. We don't want anybody to go unanswered. One question from Dave. What is the normalized energy intensity related to transformer oil tests?
Ooh, that's a good question. Let me get with Dave and find out exactly where he's going with that question. Just get a little bit deeper as far as a normalized energy intensity. All right, good question though, Dave.
What defines a qualified person able to operate 13.8 kV?
That's a real good question. Your NFPA 70E is going to give you a full paragraph of what defines a qualified person, whether it be 120 volts or a 13.8 kV line. It's all about being qualified to operate that, knowing its movements, knowing how to respond to safety, knowing the distances and boundaries, and so forth. There's a whole list of things that 70E talks about us.
We got time for one last question, Greg, and John wants to know, what are good ways in preventing DC circuit loss on a substation?
That's a good question. Let me get with John about that one and find out exactly. Let me get in with John about that on the side. It may be a little bit too complicated for the subject at hand that we're talking about, but we'll definitely get back with you, John, about that.
We want to thank everybody. That concludes our webinar today. It looks like that's about all the time we have for the presentation. We do apologize if we haven't gotten to your question today, but like I said, we will send an email that answers your questions that we didn't get to. Remember, you can view the entire webinar schedule at abotraining.com/webinars. We hope to see you at the next webinar, which we mentioned earlier about the NFPA 70E 2018 changes with Dennis Neitzel. Until then, thank you and we appreciate you listening.